welcome to lecture series on advanced linear algebra. Today I am going to talk about a new terminology, forms on inner product space. So let me first talk about that what is the motivation behind introducing this terminology. Consider V be a finite dimensional complex or real inner product space. Let T be a linear operator on it. Let f be a function from V cross V into a scalar field, say capital F, which is real or complex, and F is defined V cross 2 like this, f of alpha beta equal to inner product of T alpha beta for all alpha beta belongs to V. So, if I define a function like this, for this function we will see that for any orthonormal basis B equal to say alpha 1 to alpha n, for V the matrix of T is basically can be written as f of alpha k alpha j is equal to ajk, where the matrix representation of T with respect to this orthonormal basis, if we assume the matrix A which is equal to ajk, then we will able to express the matrix representation of the operator T in this function form. In fact, many questions related to the operator T is basically equivalent to the questions related to the function f, and f in fact determines the operator T. So, it is indirect way, this is another way to express the operator T. Sometimes you will see that to talk about the characteristic of the operator, it will be easy if I talk in terms of this function form. So, that is why I am introducing form on an inner product space. In fact, form can be introduced even other nonlinear spaces, but here we are interested on inner product space. So, what is form? Form on a vector space. Actually, this form I will say the Sesquilinear form. So, what is a Sesquilinear form on a vector space? A Sesquilinear form f on a vector space V, which is real or complex. I mean, this vector space is real complex vector space or complex vector space. So, is a function from V cross V into a scalar field, that is here real or complex, such that for any alpha, beta, gamma belongs to the vector space V, and for all scalar C may be real or complex, f of C alpha plus beta gamma equal to C of f of alpha gamma plus f of beta gamma. Second, f of alpha C beta plus gamma equal to C bar f of alpha beta plus f of alpha gamma. So, this implies f is linear with respect to first variable, whereas it is conjugate linear with respect to second variable. That is why we are saying this Sesquilinear form. This is general definition of the form on vector space. I have not mentioned whether vector space is an inner product space or not. I am simply saying that if you consider a vector space over a real or complex field, a Sesquilinear form is defined like this. In fact, if we consider the set of all Sesquilinear form now onwards only I will say forms, the form is subspace. The form is subspace of a vector space of all scalar valued functions on capital V. I mean to say, if f and g are forms on V and C be a scalar, then we can check Cf plus g is also a form on V. This part you can quickly check as a home assignment. So, I can give you as a homework, you can check it. Another interesting fact, say if the scalars are real, if the scalar field is real, then the form is linear with respect to first as well as second variables. That is, f will be bilinear. F will be bilinear. I mean, in that case, the form is called as bilinear form. Form is called as bilinear form. So, this is the general definition of forms over a vector space. but our interest is to understand the form over a finite dimensional inner product space. Specifically, our objective is to understand whether, if I consider the subspace of all forms on vector space, which is inner product vector space B, we want to know, is there any correlations between the set of all forms of a vector space and set of all linear operator on the vector space. Now, I will basically show that there exists for each form on an inner product space, there exists a linear operator on that inner product space, which are related by, if I consider the form is F on inner product space B, there will be a linear operator Tf such that f of alpha beta will be equal to inner product of Tf alpha comma beta for all alpha beta, and this Tf will be unique. So, this is our now aim to establish these results. Now, this type of results holds good also even in infinite number space, but I will limit here over the finite dimensional space only. So, this one I will prove in terms of these theorems. It is like this. Let V be a real or complex finite dimensional inner product space. Let F be a form on V. Then there exists a unique linear operator T on V such that for all alpha beta belongs to V, f of alpha beta equal to inner product of T alpha beta. Also, there exists an isomorphism between the set of all forms on V and the set of all linear operator on V, that is LVV. So, F to Tf is a basically 1-1-on-2 linear transformations between the space of all forms on vector space and set of linear operator on V, that is LVV. So, let us quickly see the proof of these results. So, let F be a form on V. So, we know from the definition of the form, for any fixed beta belongs to V, f of alpha beta is a linear function from V into the scalar field to the corresponding scalar field. I mean, it is a linear function, that is alpha to f of alpha beta for any fixed beta is a linear functional. So, this implies there exists unique beta prime belongs to V such that f of alpha beta equal to inner product of alpha beta prime. Because we know from our previous results, for any linear functionals there exists a unique element beta primes, and being such that linear functional can be written as a inner product of alpha beta prime for all alpha belongs to V. So, now consider a map U from V to V which define beta to beta prime. This implies U of beta equal to beta prime. Claim U is a linear operator. We have for any gamma and beta belongs to V, C belongs to corresponding scalar field. We have, according to our definitions, f of alpha C beta plus gamma will be equal to inner product of alpha and U of C beta plus gamma. So, this implies, so left hand side implies C bar f of alpha beta plus f of alpha gamma, which is equal to C bar inner product of alpha and U beta plus inner product of alpha and U gamma, which is equal to inner product of alpha and C U beta plus U of gamma. So, definitely this will be equal to right hand side. So, this implies that C U beta plus U gamma equal to U of C beta plus gamma. So, this implies U is a linear operator on V. And since U is a linear operator on a finite dimensional inner product space, so U star exists. So, this implies U star exists, I mean adjoint of U also exists. So, we have here f of alpha beta equal to inner product of alpha and U beta, which is equal to inner product of U star alpha and beta. Let U star equal to T. So, this implies that f of alpha beta equal to inner product of T alpha beta. Claim T is unique. Suppose there exists another linear operator T prime on V such that f of alpha beta equal to also inner product of T prime alpha beta, which is equal to T alpha beta. So, this implies that inner product of T prime minus T operating on alpha, and this is equal to 0, because both T and T prime are linear operators. So, I can use the property of the linear operator, and based on that I can like this, and this is true for all alpha belongs to V. So, this implies that T prime minus T must be equal to 0. So, this implies T prime equal to T. So, we have shown there exists a unique linear operator T associated to the form F such that F of alpha beta equal to inner product of T alpha and beta. Now, our claim is that the space of all forms on the inner product space B must be isomorphic to LVV. So, let W denote the space of all forms on V. Let psi is a map from W to LVV defined by F goes to some TF, F goes to TF. Claim psi is a 1 onto linear transformations. Let F and G belongs to W and C be a scalar, and scalar. So, psi of CF plus G, claim psi of CF plus G equal to C times psi of F plus psi of G. Now, actually the mapping F goes to TF, this implies also that for all alpha beta belongs to V, F of alpha beta must be equal to inner product of TF alpha and beta, TF of alpha and beta. We have psi of CF plus G equal to T of CF plus G. Claim T of CF plus G equal to C times T of F plus T of G. Now, CA plus G of any alpha beta belongs to B will be equal to C times F of alpha beta plus G of alpha beta. So, according to our definitions, C this one equal to C times inner product of TF alpha and beta plus inner product of TG alpha and beta, TG alpha and TG of alpha. So, this implies now CF plus G of alpha equal to like this. Okay. So, now this implies that if CF plus G goes to T of TCF plus G, this operator, this implies what? Your CF plus G of alpha beta must be equal to your inner product of TCF plus G of alpha and beta. This is like this. This is suppose 1, this is 2. So, 1 and 2 implies that I can say, just simplify the one more step, this is equal to C times TF of alpha plus TG of alpha comma beta. Okay. So, I can see that inner product of TCF plus G of alpha and beta equal to C TF of alpha plus TG of alpha and beta. So, this implies that TCF plus G equal to C of TF plus TG, because this is equal to C TF plus TG of alpha. So, this implies the map, this implies psi is a linear transformation. Okay. Now, claim is psi is 1 1, claim psi is 1 1. We have for any f belongs to W, psi of f equal to T of f. So, this implies that f of alpha beta equal to inner product of T f of alpha comma beta. So, if psi of f equal to 0, this implies f of alpha beta equal to 0 equal to T f alpha. For all alpha beta belongs to V. If psi f equal to 0 implies f of alpha beta equal to 0 equal to this one. So, this implies that T f must be equal to 0. So, psi is 1 1, since psi is defined over two finite dimensional vector space. So, therefore, psi is also on 2. Since dimension of W, since dimension of W and dimension of LVV is finite. So, 1 1 implies on 2 also. So, psi is an isomorphism between W and LVV. So, we see that for each form on a finite dimensional inner product space, there exists a unique linear operator T such that f of alpha beta equal to inner product of T alpha and beta. In fact, due to this isomorphisms between the W and LVV, we can also say one nice result. It is like this: if f and g be any elements of W and Tf Tg are the corresponding linear operators, then one can introduce an inner product on this space W, then inner product of f and g equal to trace of Tf and Tg star for any orthonormal basis B equal to alpha 1, alpha 2, alpha n with the property T that inner product of f and g equal to j and k, f of alpha k, alpha j and g of alpha k, alpha j bar. This is equal to 1 to n. I mean j and k both variables are varying from 1 to n. The inner product of f and g can be written like this thing. The proof of this result is also very straightforward. Since we know trace of Tf and Tg star is an inner product on LVV. I mean to say that is the functions TFTG goes to, the map TFTG goes to trace of TFTG star is an inner product on LVV, because we know inner product is also a function from LVV cross LVV, okay, to some scalar value, to real or complex number. So, like this. This implies that inner product of F and G can be written as trace of TF and TG star. Inner product can be written like this, because you know there is a 1-to-1 relation between the set of all forms on V and LVV. In particular, if I consider, let B equal to alpha 1, alpha 2, alpha n be an orthonormal basis for V, and the matrix representation of TF with respect to B equal to say capital A, and matrix representation of the operator TG with respect to order basis B equal to say capital B, then we have inner product of T of alpha, TF of alpha k and alpha j. What is this? So, this will be equal to, we will have inner product of TF of, say, TF of alpha k will be equal to sigma, according to the definition of the matrix representation, we have TF of alpha k will be equal to AI k, I equal to 1 to n. I mean to say, we have to consider the kth column vector of the matrix A times alpha I and alpha j. So, this is equal to, according to the definition of inner product, I will have this is equal to sigma A I k and delta I j. This is I equal to 1 to n. So, this is equal to simply A j k. This will be A j k. So, this implies that the matrix A equal to A j k, which is A j k is equal to like this. So, this implies f of alpha k and alpha j, because when I equal to j, then only I will have 1, otherwise 0. So, I will have this will be equal to A of j k alpha j and alpha j. Okay. So, I will have like this, because f of alpha k alpha j is equal to inner product of T of alpha k and alpha j. So, we have like this. Similarly, Bjk of matrix B is given by, and Bjk will be equal to inner product of Tg alpha k and alpha j. So, this implies trace of A B star, which is equal to sigma j equal to 1 to n A B star of j j, which is equal to sigma j as well as I can say k A j k and B star k j, okay, and this is equal to Ajk and Bjk bar, and this is equal to sigma over j and k. Ajk equal to, we know, f of alpha k and alpha j and g of alpha k and alpha j bar. Now, let us see whether we can define a matrix representation of the form or not. As we know, the operator T defined over a finite dimensional vector space, one can have a matrix representation of the operator with respect to a given order basis. So, similar concept also can be introduced for the forms. So, matrix representation of form, but this is basically valid only for finite dimensional space. Let V be a real or complex finite dimensional inner product spaces, inner product space. Let F be a form on V. Let B equal to alpha 1, alpha 2, alpha n be any order basis for capital V. So, I have not taken here this basis as an orthonormal basis, I have taken simply an order basis. Then Ajk equal to f of alpha k and alpha j. So, if I define like this, Ajk equal to like this for 1 less than or equal to j less than or equal to n and 1 less than or equal to k less than or equal to n, gives the matrix representation of f with respect to order basis B. The matrix representation of a form may not be same the matrix representation of the corresponding linear operator. They will be equal if we consider order basis as an orthonormal basis. Otherwise, the matrix representation of form will different from the matrix representation of the corresponding operator. Let me define another terminology called Hermitian form. Let V be a finite dimensional real or complex inner product space. Let F be a form on it. F is said to be a Hermitian form provided for all alpha beta belongs to V, f of alpha beta equal to f of beta alpha bar. So, this implies if T denote the corresponding linear operator, that is f of alpha beta equal to inner product of T alpha beta, then we have f of alpha beta which is equal to inner product of T alpha beta, and this is also equal to f of beta alpha bar, f of beta alpha bar equal to inner product of T beta alpha bar, which is equal to inner product of alpha and T beta. So, this implies that inner product of T alpha beta equal to inner product of alpha T beta, implies T is self adjoint, that is Hermitian. So, if the form is Hermitian, then associated operator is also Hermitian. So, this gives a nice clue to establish a nice result, that is called principal axis theorems. What is that? Principal axis theorem. It says that let V be a finite dimensional real or complex inner product space. Let F be a Hermitian form. On V. So, let V be a finite dimensional real or complex inner product space. Let F be a Hermitian form on V. Then there exists an orthonormal basis for the space V such that the matrix representation of F with respect to B is a diagonal matrix. Now, matrix with real entries on the main diagonal. The proof of this result is basically application of the what we have already learned. Let T be the corresponding linear operator, that is f of alpha beta equal to inner product of T alpha beta. We know T is Hermitian since F is Hermitian. So, there exists an orthonormal basis B equal to something like that alpha 1, alpha 2, alpha n for V consists of eigenvectors of T. That is, there exist n scalars C1, C2 and Cn such that T of alpha I equal to Ci alpha I. Since T is self adjoint, each Ci is real. Already we have proved, because self adjoint operator having eigenvalues are real. So, this implies if I consider the matrix representation of the form F with respect to this order basis, I have f of alpha k alpha j equal to inner product of T of alpha k alpha j, which is equal to inner product of C k alpha k and alpha j. So, this is equal to C k and delta k j. Okay. Since alpha 1, alpha 2, alpha n, this is a orthonormal basis. So, it will be basically like this. This is delta k j is a Kronecker delta, that is equal to 1 if k equal to j. So, this implies if matrix representation of f with respect to order basis B is capital A, then AJK equal to we have CK delta Kj. So, this implies A is a diagonal matrix with real entry on main diagonal. Friends, this is a nice results which will be utilized to solve many problems in terms of quadratic forms, positive forms, in other different forms. However, due to time limitations, I could not talk many more interesting results, but I have initiated what I promised in my promo. I hope this initiation will help you to face all the endeavors related to linear algebra problems, all the problems related to linear algebra when you face in your different areas. I am sure this will definitely help you and boost you. All the best.